Have you ever wondered how a self-driving car knows exactly how far away the car in front of it is? Or how a robot can navigate a cluttered room without bumping into everything? Well, it's not magic. It's actually a brilliant trick that's been borrowed directly from nature, and it all starts with having two eyes. Today, we are going to break down stereo vision, the simple but super powerful method that lets robots see the world in 3 dimensions, just like you and me.
All right, let's dive right in. To really get why stereo vision is so cool, we first have to understand the problem it solves. Why isn't just one camera, one eye, good enough for a robot?
I mean, it's the big question, right? Nature gave most predators two forward-facing eyes for a very good reason. And it's the same reason engineers are copying that design for their robots. So let's see why. Because with a single camera, the world is just a picture. It's totally flat. There's no sense of depth. So a robot might see a coffee cup, sure, but it has absolutely no idea if that cup is a foot away or 10 feet away. To the robot, it's all just a bunch of pixels on a sensor. And this, as you can imagine, leads to some, well, pretty clumsy moments. Picture a robot arm reaching out with all the confidence in the world to grab your morning coffee and just completely whiffing it because it had no idea how far to reach. That is the one-eyed robot problem in a nutshell, a total lack of depth perception. So how do we fix this? Well, believe it or not, your own brain is running this incredible 3D algorithm, like all the time, without you even thinking about it. Let's actually see it in action with a super quick experiment you can do right now.
Go on, give it a shot. Hold your thumb up, maybe a few inches from your face. Now close your left eye and look at your thumb. Now switch, close your right eye and open your left. See that? See how the background behind your thumb seems to jump from side to side? That little jump? That's everything.
So that jump you just saw, it has a name. It's called disparity, and it is the key piece of the puzzle. Now try this. Hold your thumb all the way out at arm's length and do it again. The jump is way smaller, right? Your brain knows this instinctively. A big jump means the object is close, and a small jump means it's far away. Okay, so how does a robot do what your brain does intuitively? Well, it does the exact same thing, but it translates that jump into cold, hard math. And you know what? It all comes down to one surprisingly simple equation. To make this work, we just need 3 key ingredients. First up is the baseline. That's just a fancy word for the distance between the two cameras. For us humans, it's the distance between our eyes, about 6.5 centimeters. A robot might have a much wider baseline to help it see depth further away. Second, we need the focal length. The easiest way to think about this is it's just a property of the camera lens. It basically tells you how zoomed in its view of the world is. It's a fixed number for a given camera. And number 3, our star player is back. Disparity. But for a robot, this isn't some vague feeling of a jump. It's a hard number. It's the exact number of pixels that an object shifts between the image from the left camera and the image from the right camera. And here it is. This is the whole secret recipe. The depth, which we'll call z, is simply the focal length times the baseline, all of that divided by the disparity. That's it. That's how a robot turns a simple pixel shift into a real-world distance measurement. So let's plug in some numbers. Let's say a robot's cameras see an object with a disparity of 50 pixels. The equation spits out that the object is exactly 1.2 meters away. Now, what if that same object had a disparity of 100 pixels? A much bigger jump. Well, the robot would calculate it's only 0.6 meters away. See? Double the disparity, half the distance. It just works. So the theory is really elegant, right? But putting it into practice in the real world, well, that involves a few critical steps. And it also reveals some kind of hilarious ways this whole thing can fail. Okay, so here's the process. First, the robot has to perfectly align the two camera images. Then comes the really hard part. For every single point in the left image, it has to find the exact same point in the right image. Once it finds a match, it measures the disparity, plugs it into our magic equation, and then it does that over and over for the entire image to build a complete 3D depth map of the world. But here's where things get tricky. What happens if the robot looks at a blank white wall? There are no features to match. The algorithm gets confused because every white pixel looks like every other white pixel, so it can't find a match, it assumes the disparity is 0, and the equation tells it the wall must be infinitely far away right before it drives straight into it. Repeating patterns are just as bad, if not worse. Imagine a picket fence. The algorithm sees a fence post in the left image and tries to find it in the right image, but there are like a dozen identical looking posts. It very often picks the wrong one, which results in these bizarre, wavy, completely hallucinated 3D shapes. And finally, shiny or transparent stuff is a total nightmare. A robot looking at a glass window doesn't really see the glass itself. It sees the reflection or it sees the room behind the glass. So it starts matching those background objects, becoming completely blind to the sheet of glass that's right there in front of its face. Now, even with all these weird quirks, stereo vision is an incredibly powerful and really widespread technology. In fact, you've almost certainly used it or benefited from it today without even knowing. Now, it really comes in two main flavors. There's passive stereo, which is what we've been talking about. It just uses whatever light is already in the room, just like our eyes do. But a lot of devices like your phone, what it unlocks with your face, kind of cheat by using active stereo. They actually project their own invisible pattern of infrared dots onto the world. This makes finding matching points super easy, even if you're in a pitch black room. And seriously, once you know what to look for, you see this technology everywhere. It's in cars for driver assistance, in those robot dogs that can navigate crazy terrain, it's in robot vacuums so they don't fall down the stairs, in drones for avoiding trees, and it's even in VR headsets to map your room so you don't run into your couch. It's just such an elegant and powerful solution that has totally changed how machines see our world. But it does leave you with a fascinating final thought. If two cameras are this good, what new kinds of possibilities open up when you add a third?